Acid-base balance is a tightly regulated process. Normal body pH ranges between 7.35 and 7.45, equating to a difference of just 9.2 nanomoles per litre. Compensation is the expression used to describe the body's response to the introduction of a process that generates either an alkalosis or an acidosis. Without these compensatory mechanisms, pH would rapidly escape its normal boundaries, disrupting many biochemical processes. This tutorial will cover the processes employed by the body to compensate for acute acid-base disturbances, and will describe how an assessment of the adequacy of compensation can be made. Compensation should be differentiated from the actions of a buffer. A buffer solution is an aqueous solution of a weak acid with its conjugate base, or a weak base with its conjugate acid. Buffers are unique solutions in that when small quantities of a strong acid or base are added to the solution, the pH changes little. pH is affected least when the solution is at a pH around the pKa of the buffer solution. The best known physiological buffer is the carbonic acid system. When hydrogen ions are added to the system, the reaction is driven to the left, resulting in some absorption of protons. Compensation can only occur because the acid-base system is open. In a closed system, the total number of atoms before the reaction is the same as the total number after. In contrast, the body's acid-base system is open in that CO2 and bicarbonate can be added or removed from the body. In this way, the body can remove the 50 to 100 milliequivalents generated by metabolism and the 12,000 millimoles of carbon dioxide produced every day. Compensation is the body's ability to further regulate the shift of carbon dioxide, protons and bicarbonate into or out of the system when disturbances in the acid-base balance arise. Importantly, it is rare for the pH to return to 7.40. Assessing the appropriateness of compensation is a difficult process and relies on complex rules, some of which follow this section. The importance of assessing compensation is that it may help to reveal the presence of additional pathologies which disrupt the compensation process. When there is an acid-base disturbance related to the accumulation or excretion of carbon dioxide, the disorder is referred to as a respiratory disorder. The body will respond to this process with metabolic compensation, which is largely regulated by the kidney. For example, in respiratory acidosis, the body generates a competing metabolic alkalosis that returns the pH towards 7.4. The metabolic response to acid-base problems can be divided into acute and chronic. Initial compensation can usually be seen within 12 hours of onset, while chronic compensation may take days to fully develop. The adequacy of the compensation can be assessed by a series of complicated rules, but the simplest is the 1, 2, 3, 4 rule. Under this rule, for every 10 millimeters of mercury that the CO2 changes, the bicarbonate will change based on the following. Acute acidosis, increase 1 millimole per litre. Acute alkalosis, decrease 2 millimoles per litre. Chronic acidosis, increase 3 to 3.5 millimoles per litre. Chronic alkalosis, decrease 4 to 5 millimoles per litre. Stimulation of the brainstem respiratory centre by increased hydrogen ion concentrations results in a powerful stimulus for respiration. For metabolic disorders of acid-base balance, the body can regulate the impact of pH by increasing or decreasing the excretion of CO2. Complicated rules exist, but an easy rule of thumb to follow is as follows. Between the pH of 7.10 and 7.55, the partial pressure of CO2 will be the same as the first two digits after the decimal point of the pH. For example, if the pH was 7.22, the carbon dioxide would be expected to be 21 to 23 millimetres of mercury. A higher pH would suggest overcompensation, i.e. a superimposed respiratory alkalosis, while a lower pH may suggest a simultaneous respiratory acidosis. More sophisticated compensation rules have been developed. Two schools of thought on these rules have evolved, commonly referred to as the Boston approach and the Copenhagen school. The former bases compensation rules on the estimated bicarbonate, while the latter uses base excess. The Boston group argued that their rules are easy to apply and are based on real-world, in vivo experiments. It should be noted that the 1, 2, 3, 4 rule of respiratory acid-base disturbances are also Boston rules. Proponents of the Copenhagen model argue that the bicarbonate is not the only buffer that interacts with metabolic acids, nor is it independent from changes in PaCO2. As such, the base excess, which more directly measures titratable acid, is a better measure of the magnitude of the disorder. In this case example, an elderly woman with multiple comorbid problems is admitted to a hospital with persistent vomiting. The following blood gas results are obtained. The results demonstrate a marked alkalemia. An interpretation of the CO2 and bicarbonate suggests this is a metabolic alkalosis. From the rules presented above, her expected CO2 is 52, as calculated by the Boston rules. The Copenhagen rules suggest that the change in her CO2 will be 9 millimetres of mercury. Assuming the starting point for her CO2 was 40, her corrected CO2 will be 49 millimetres of mercury.